Hello everyone, this is data mining class and I am Sherry Sahebi. Today we are going to talk about dimensionality reduction. So we know the problems of working with data that is high dimensional. We know that when data is high dimensional, as d, where the dimensionality of data goes to infinity, we are going to have exponential number of corners in different dimensions. And we can see that most of the space, as d goes to the infinity, is going to be in the corners. And we are going to have infinite number of diagonals in the space that they are all orthogonal to each other. So the vectors or the data that are going to be in the corners are all orthogonal to the axis and to each other. So as a result, all the angles and distances are going to be similar in the dimensional data with high D. And then it is going to be really hard for us to find patterns in the data. For example, it's going to be hard to detect clusters. It's going to be difficult to build classifiers to understand what class each data belongs to, et cetera, et cetera. And we have seen that like examples exist, like normal distribution, that this happens. And now today we are going to talk about dimensionality reduction. That is a way to kind of alleviate this problem. So in dimensionality reduction, we assume that we have data in small d dimensions, and what we assume is that although our space is d-dimensional, although we have d features or characteristics from the data, but it's not that we really need all of these features, or in other words, our data is not d-dimensional. It can be summarized in lower dimensions. So basically, we assume that our data lies on a lower dimensional subspace of this original subspace that original space that we had. And then the axes of our data are going to be, this subspace are going to be an effective representation of our data. So for example, suppose that we have a two-dimensional data, so one attribute x1 and another attribute x2. And then assume that our data points are like this. So these are the data points that I have in my data set. So what I see is that I have, for each data point, I have two attributes. I have x1 and I do have x2 also, right? But if we look closely to this data, we can see that all of these points are lying on the same line, that is this purple line, right? In that case, we may think that, okay, I can actually represent my data using this purple line only. I don't need both to represent my data in these two spaces. I can create a new feature. Let's call it U1, okay? And I can say, I can talk about my data points in terms of U1 instead of in terms of X1 and X2. So for example, if this first data point has x1, 1 and x2, 1, this one has x1, 2 and x2, 2. So my data in original x1, x2 space looks like 1, 1, 2, 2, 3, 3, etc., etc. Instead of showing my data in this space, I can just use U1. And then I can say my data, the same data points that I have, are going to be 1U1, 2, 3, etc., etc. So something like this. Why is this happening? Because my data here is following a structure that is lower dimensional. I can represent all of my data on this line. Even if all of my data points are not falling on the line, if they closely follow some shape similar to a line, like what we see in here, still we can capture a lot of variation in our data by just using a line. So here in this picture on the left, you can see that our data points, the purple circles, they are not exactly falling on the line, but they are close to this line. And having this red line, we can explain our data in a reasonable or acceptable way. Or in this picture on the right, our original space is three-dimensional. So we have three features, for example, in this space. But then we can see that our data points are more or less falling on a plane, which is two-dimensional. So using these two red axes, we can represent our data good enough that we don't need all three axes. So the goal of the dimensionality reduction is basically to find out all of these axes in lower dimensions that can explain our data good enough or well enough. Let's see another example of dimensionality reduction. So suppose that we are looking at the sales of of a company, and the sales is our data. So we have a data table for each customer. We have in which day of the week or which date we have sold how much of our product. Now, listing our customer as our data table. So each customer is going to be one data point, and each of the days of the week is going to be one feature for us. So for example, here we can see that ABC Inc., we sold one item on Wednesday, one on Thursday, one on Friday, and on Saturday, Sunday, we didn't sell anything. So for another company, we sold two items on Wednesday, Thursday, and Friday, and Saturday and Sunday we didn't sell anything. Now, if we look at the last row, Thompson, we can see that on Wednesday, Thursday, Friday, we didn't sell anything to that customer, but on Saturday, Sunday, we sold one item each. So if we look at the whole table, we can see a kind of a pattern in this data. Can you think of the pattern? Yeah. So the pattern is that in these last three data points or companies that we have, customers that we had, on Wednesday, Thursday, and Friday, we didn't sell anything to them, right? And whatever we sold was on Saturday, Sunday. But to the first four customers, whatever we sold, we didn't sell anything on Saturday and Sunday. Whatever we sold was on Wednesday, Thursday, and Friday. Okay, so that's one pattern that we are seeing here. Another pattern that we can see is that whatever that we are selling to the first four companies are the same multiplications of one. They are all the same. So for example, to ABC, we are always selling one item per day on the days that we are selling things. Or on DEF, we are always selling two items per day. So it's always equal. On the days that we are selling things, it's always an equal number. It's similar for the last three also. So if we sell something to Smith, it's always two. If we sell something to Johnson, it's always three, right? So basically, we can see that our data, although we have like this bigger table, but we can somehow summarize our data. So if, for example, I split my days of the week into two, so I would say Wednesday, Thursday, Friday here, and then Saturday, Sunday here, I can simply say that ABC has 1 here, 0 here, 2, 0, 1, 0, 5, 0, right? This is for the first 4. And then for the next 3, it's 0, 2, 0, 3, 0, 1, right? This is exactly a summary of our data that we have in that table. Now, how can we actually show that? Well, let's look at our dimensions or features. So in the data table, we can see that each row or each data point is a vector, is a d-dimensional vector, right? Our d is how many? 1, 2, 3, 4, 5, right? We start with a 5-dimensional vector, which is the number of features for our data points, and we are getting to a d equals to 2-dimensional vector when we are summarizing, right? So what we can think of is that our original space has 5 dimensions, or let's say 5 axes, and our new space has only 2 axes or 2 dimensions. How can I represent these new 2 axes? My representation of 2 axes are actually summarized here, right? This shows that my first axis is 1 on Wednesday, 1 on Thursday, 1 on Friday, and 0, 0 for Saturday, Sunday. And my second axis, or my second dimension, is 0, 0, 0, 1, 1, right? Because Saturday and Sunday are 1. So basically, suppose that I'm looking at Smith here. So Smith, in the original space, is a vector, is a 5-dimensional vector. Its values are 0, 0, 0, 2, 2, right? But I can write Smith as a combination of these new axes that I have. I can say Smith is equal to 0 multiplied by my Wednesday, Thursday, Friday, so 1, 1, 1, 0, 0, plus 2 multiplied by my new Saturday, Sunday axis, 0, 0, 0, 1, 1, right? And then that is going to be giving me my Smith. Okay, so basically we went from a 5-dimensional matrix to a 2-dimensional matrix without losing any information. Okay, how can we actually explain this mathematically? What can explain this to us is rank of our data matrix. So what is the rank of a matrix A? Rank is the number of linearly independent columns of matrix A. Or also, it can be the number of linearly independent rows of A. So if I have an N by D matrix, rank of A is either the number of columns that are independent, linearly independent, or the number of rows that are linearly independent. So rank of A is going to be less than or equal to minimum of number of rows and columns, right? Okay, so for example, look at this matrix that we have. You should know this from linear algebra, but just to remind you, we have this matrix A that we have here. It has values 1, 2, 1 in the first row, -2, -3, 1 in the second row, 3, 5, 0 in the third row. This is a 3 by 3 matrix, right? And if I want to look at it as a data matrix, I can say that it is represented in a 3-dimensional space, right? Because I have 3 features. Now, although it is in a 3-dimensional space, the rank of this matrix is 2. Why? Because I can only find 2 linearly independent columns or rows in this matrix. The third row, for example, can be written as a linear combination of the other 2. So here, for example, we can see that the third row here, 3, 5, 0 can be written as a linear combination of the first row, 1, 2, 1, and the second row, -2, -3, 1. What is a linear combination? So a linear combination is basically a weighted sum, right? So it's like there is some value A1 that I can multiply by the first row plus some other value A2 that I can multiply by the second row, and I sum these two and I get to the third row. What are A1 and A2? For example, if A1 is 1 and A2 is -1, I can get the, so 1 multiplied by the first row minus 1 multiplied by the second row is going to give me the last row of this matrix. So I can write the third row according to a linear combination of row 1 and row 2. So the rank is not 3, the rank is 2. Now, can I go lower than 2? Can I have a rank 1 in this matrix? Let's check. If I can find a linear relationship between row 1 and row 2, then yes, I will have rank 1. But then we can see that there's no way that we can linearly write row 1 according to row 2 or the other way around. So we need at least these 2 rows to be able to represent the whole matrix. So the rank of this matrix is exactly 2. Now, why do we say that the rank of a matrix is important for us in this case? It's because the rows that make the rank of a matrix can be a basis or the new axis for us in a lower dimensional space. So we have this matrix A, and we are representing it in 3 dimensions, right? However, I'm telling you that we can rewrite A as in 2 dimensions, 2 being the rank of A instead of 3, and then we are not going to lose any information. How? We can have these 2 vectors, the first row and the second row, as the new basis vectors. So our A is going to be 2-dimensional matrix, right? For example, x1, x2. x1 is 1, 2, 1. x2 is -2, -3, 1. And then I can see each row of A is how much of x1 and how much of x2. So the first row of A is 1x1 and 0x2, right? I can write because it's equal to x1. The second one is 0x1, 1x2, okay? The third one, we already see it is a linear combination of x1 and x2. It's 1x1 and -1 x2, right? So basically, I could write matrix A, which was in the 3-dimensional space, as a new matrix A in a 2-dimensional space, but my new basis vectors, my new axes, are x1 and x2, that are these 2 now. So basically, rank is our dimensionality. So when we are in this new lower dimensional space, we are using the lower rank representation of our data in it. So our old basis vectors, when we have this old matrix A, are going to be standard basis vectors. You remember standard basis vectors from linear algebra, right? So in the old world, what we had was, let's say, x1, x2, and x3, and our basis vectors are the standard basis vectors are the ones that are 0 everywhere except in one of the axes, right? So we have E1, E2, and E3 as our basis vectors that basically show us the direction of axis 1, axis 2, axis 3, and they have length 1. Now, if I want to represent point C in our original space, it has dimensions 3, 5, and 0, right? So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So our C actually in the original space is going to be here. This is C. Where is B? B is -2, -3, 1. So this is -2. This is -3, and 1 is here. So it's going to be somewhere, for example, here. This is B. And A is 1 to 1. So 1 and 2, and 1 here, for example, A. Okay? So this is representation of my matrix in the original space. Then we saw that we can have the two vectors A and B as our new new axis. So we are going to have this and this as our new dimensions. Now, if I have these two as my new dimensions, what I can do is that I can represent C in terms of these new coordinates. And C in terms of these new coordinates is going to have values 1 and -1. Okay, so these are going to be my new coordinates for C in this space that are represented by A and B points. Okay. So we have two new basis vectors, and we are representing C in terms of two coordinates that are our new coordinates that are 1 - 1 in these new basis vectors space. So we reduce the number of coordinates here. So to summarize again, the goal of dimensionality reduction is to find out a new axis or multiple new axes that represent our data the best. Instead of, for example, representing every data point in two coordinates, 2 dimensions, 2 axes, two features, we represent each data point with 1 coordinate, right? Now, again, you remember the first picture that I showed you, our data may not exactly lie on the line that we want to see. So, for example, our data may be a little bit farther from this line that we use to represent our data in lower dimension. In that case, we are seeing a little bit of an error, and we say that's fine. We are going to tolerate that. The representation that we have is not exactly the same as the original data, but then we are going to have a summarized representation. So we are okay with a little bit of an error, but we want a summarized representation of our data, and then it would be easier to handle our data. So again, why do we want to reduce dimensionality? Because first of all, it's going to be easier to handle. So we will have an easier time to work with the data. But also there are other reasons. You remember here, when we had our customers table, we kind of summarized our data in a new two-dimensional representation. So that's another way we can have a summarized representation of our data. But also we discovered pattern in our data when we represented it in lower dimensions, right? We discovered this pattern that some of the sales only happen on Sunday, Saturday, and some others only happen on Wednesday, Thursday, Friday. So there were these hidden patterns in our data that we could discover by using dimensionality reduction. So basically, that's another good thing. Another good thing is that sometimes our data is noisy. So although we are tolerating some error to reduce the dimensionality of the data, but also that error may be because our data collection has been noisy. So by reducing the dimensionality and getting rid of that error, we are getting rid of the noise in the data. Well, of course, it will be easier to interpret and visualize the data when we reduce the dimensionality, right? So when you have 4 dimensions, 5 dimensions, 10 dimensions, it's not easy to visualize that. We can only visualize up to 3, right? So we can summarize our data in 3 dimensions or 2 dimensions and then visualize it. So all of these are the reasons that we do reduce dimensionality. So formally, the goal of dimensionality reduction is to find a lower dimensional representation of data matrix that we had. So our data matrix D, that originally is N by D, we want to find a lower dimensionality representation of this data. For example, we want to find an N by R dimensional matrix that represent our data matrix D, and R is smaller than D. Okay. So when we have this D data matrix, what does it look like? We have N data points and D attributes, right? So each of my data points, let's call them xi, is going to be a vector that has values xi1, xi2, etc., xid in it, right? So this is each data point that we have in the original d-dimensional vector space. Now, when we say that our data vector has these values, xi1, xi2, etc., until xid, what is the geometric interpretation of that? The geometric interpretation of that is that the data vector xi in the axis, in the first axis that is represented by the first standard basis vector, 1, 0, 0, 0, like a d-dimensional, that is called E1. It is an xi1 scale of the standard basis vector E1. So it's as if we are stretching E1 xi1 times. We are stretching E2, the second basis vector that represents our second axis or second data feature, xi2 times, etc., etc., to build our data vector xi itself, right? So basically it means that we can rewrite our data vector xi in the original d-dimensional space like this. We can say it's a linear combination of our standard basis vectors, right? It's equal to xi1 multiplied by vector e1 plus xi2 multiplied by vector e2 plus xi3 multiplied by vector e3 plus etc., etc., until xid multiplied by vector ED, right? So this is how we have been representing our data points in the D-dimensional space so far. But also, if we are given another set of vectors, D vectors, that are orthonormal, meaning that they are orthogonal to each other and they have a length of 1, then we can again rewrite xi in terms of those D vectors. So, meaning that, suppose that our original data space is two-dimensional. I have, this is the direction of E1. So E1 is this. This is the direction of E2, right? X1, X2. And if this is my X data point, X1, for example, I can say that it's equal to 2.5 E1 and 2 E2, right? So I can rewrite X1 like this. I can say X1 is equal to 2.5 vector E1 plus 2 vector E2. This is my X1 vector or X1 data point. But if someone gives me another set of axes that are orthogonal to each other. So for example, suppose that I am given, this is U1 and this one is U2, then I can actually see, I can project my X1 into U1 and U2, right? This is the new coordinate for X1 on U2. And this is the new coordinate for X1 on, U1 and U2. So for example, this is going to be 3 and this is going to be -1. Then I can again write X1, vector X1, as 3 multiplied by vector U1 plus -1 multiplied by vector U2, right? So this X1, my X1, they are both the same. The only difference is that I am writing them in different axes, and as a result, they are having different coordinates in these two different axes for me, right? So basically, I can write my data as a linear combination of these new orthonormal axes, and each of these A1, A2 until AD are going to be my new coordinates of our each data point X. So we say that A, vector A, that has all of these A1, A2, AD in it, is the coordinates of X in the new basis. And if we put all of these U1 and U2 until UD into a matrix, so we have a matrix U and we have U1 here, U2 here until UD here, because they are vectors themselves, right? We can say that X is actually a multiplication of matrix U with vector A. Okay. So U is a D by D matrix. Each column is the coordinates or the direction of U1 in the original space, the dimensional space, and it shows the basis vector UI for us. Now, because all of these UIs are orthonormal to each other, it means that the inverse of matrix U is actually equal to U transpose. So inverse of U is equal to transpose of U. And then we had that X is equal to UA, right? X is equal to vector X is equal to matrix U multiplied by vector A. Now, if I multiply both sides of this with U minus 1, I'm going to have U minus 1X is equal to U minus 1 UA. And then what we can say is that because U minus 1 and U is actually equal to identity matrix, and this will be equal to A, and we know that U minus 1 is actually equal to U transpose, we can conclude that vector A is equal to U transpose X. Okay, so what are we doing here? What we are doing is that basically it means that if you are given an original data point X, a data point X that is represented as a vector in the original V-dimensional space, and then you are given a new basis, a new set of orthonormal vectors, U1 to UD as the new basis, then you can calculate the new coordinates of our vector X in this new D-dimensional space U like this. You can just multiply U transpose with X and get to the new coordinates. So for example, basically in our example, you can get to 3 and minus 1. Basically, you are going to get to 3 and minus 1 by multiplying U1, U2 with 2.5 and 2. Okay. All right, so let's see an example. So we have a data matrix D in a two-dimensional space with the basis vectors E1 and E2. So we have 3 data points and 2 axes. And we want to transform D into a new coordinate system with orthonormal vectors. U1 is this one and U2 is this one. So we said that the new coordinate system for each of our data points is going to be equal to U transpose X, the original data point, right? So for example, suppose that I'm looking at the second data point. So my X is minus 2, minus 1.5, and my U, I put the two vectors next to each other is negative 1 over square root of 2, 1 over square root of 2, and 1 over square root of 2, 1 over square root of 2. Now U transpose is the transpose of that matrix, right? So it's going to be 1 over square root of 2 minus 1 over square root of 2. So this is minus, this is 1 over square root of 2, 1 over square root of 2, 1 over square root of 2. I think so. Let's see. Yeah. And then we calculate A as a multiplication of U transpose and original X. And if we do that, we are going to get to this new matrix. So our new A2 for the second data point that we had is going to be 0.35 minus 2.47. If we actually look at it geometrically, so our D was what? 1, 1, minus 2, minus 1.5, and 0, 1. Our D was in the original space that was spanned by E1 and E2, right? So E1 and E2. And our data points were what? The first data point that we had, this is 1, 1, the first data point. The second one that we had was minus 2, minus 1.5. So for example, here, this was the second data point. And the third one was 0 and 1. This was the third one in the original space. Now, our new directions, U1, U2, were basically like this. We're in these two directions. Okay. So this was, for example, oops, this was U1. It was minus 1 over square root of 2, positive 1 over square root of 2. So this was my U1, and then this was my U2. Now, for this data point, I can actually calculate the new coordinates of this data point in this new system, and that's going to be minus 2.47 U2 and 0.35 U1. Okay, that's what we have done. Now, okay, so we know that if we have these two original bases, and then we have data points in these two original bases, we are given two new bases, we can actually calculate the new coordinates. But don't forget our goal. Our goal was to find the best directions to represent our data. But I can have infinite number of orthonormal basis vectors for my space. Why? Because although this is U1 and U2, I can have, like, for example, these two to be my U1 and U2. It's enough that they have a 90-degree angle and then they are of length 1. Or I can have, for example, these two, right? I can just rotate my axis, my coordinate system, and have infinite number of orthonormal basis vectors that I can project my data onto. But our goal is to find the direction that gives us an optimal basis. And also, we want to reduce that number of bases that we need to represent our data, right? So our interest is finding the optimal R-dimensional representation of our data with an R that is much less than D. Basically, it means that instead of having D different U's, U1, U2 until UD, we only have R different U's, or new orthonormal basis vectors that can represent our data. So in other words, if I'm given these new R basis vectors, I should be able to represent my data point x by projecting it into these R new basis vectors, right? So my x prime, which is the projection of my data point onto these R basis vectors, is going to be equal to multiplication of these coordinates, new coordinates A1 to AR, with the new basis vectors U1 through UR that I can represent like this, right? So basically it means that my original data point is d-dimensional, so x is a d-dimensional vector, and I want to get x prime, which is projection of x in R-dimensional space. And my x prime is going to have coordinates that are new coordinates A. So that's why we can say x prime is equal to UR, which is like putting all these are new orthonormal basis vectors next to each other, multiplied by the coordinates AR. Similar to what we have seen previously, we can say that our AR, we can calculate that using UR transpose, which is equal to UR minus 1, or inverse of UR, multiplied by X. AR is an R-dimensional vector, so it's basically R by 1. UR is R by D, and X is D by 1. Okay, so that is basically our goal, to find UR. And also we can rewrite X prime, because we know AR is U transpose X, right? To be equal to, putting these two together, it's going to be equal to UR multiplied by, instead of AR, we can write this, multiplied by UR transpose X, right? Okay, so let's call this UR transpose a new matrix PR. This PR, it's an R by R dimensional, it's a D by D dimensional matrix that we call it the orthogonal projection matrix for the subspace that is spanned by these R basis vectors. Okay, so what are we doing here? What we are doing is that this is our original space, for example, and this is our new space, new R dimensional space. So let's, because R is less than D, let's just remove this one. So suppose that I have a data point. This is my X. It's represented in 2 dimensions. Now, what I can do is that I can project my X into this new coordinate system, and this is going to be my A in this direction, right? So for example, my X is equal to 1 and 2. A is going to be equal to 3, right? X is 1 and 2. A is 3 in the new dimensional space. But also I can see A as a point in the original space, right? So I can say A is actually an X prime in the original space. Now X prime in the original space is, for example, 1.5, 1.5, right? So you can see how we can get from X to X prime, which is X prime is actually a representation, the projected representation of our original data point onto the new space, but represented in the original D dimensions again. Okay. All right. So what we can do is that we can say, okay, so now that I have had X in the original space and I got A in the new space, we said that we are losing some information. We are having some error at some point, right? So what is the error? We said that because our data, original data X is not exactly lying on this vector U, right? So if I am representing X by A, I have this much of error, right? From here to here, I'm just losing this information. How can I measure this? I can measure it by subtracting X prime from X, right? In the original space that we are, because we cannot compare A with X directly because it's going to be apples and oranges. A is represented in a new basis vector dimension. It's a new coordinate system. So I cannot compare A with X directly, but I can compare X prime with X, right? So I can see how much X is different from X prime. And then I can say, okay, after I project X into this new coordinate system, I get this much of an error. I lose this much information, or I get this much of an error. So the vector, the error vector that I'm having is, let's call it epsilon. It's going to be a vector, or actually it's orange. Epsilon is a vector that is basically equal to the difference between the original X minus the new X prime. So mathematically, this is basically equal to X minus PR X, right? PR being, here we have seen that, PR being UR multiplied by UR transpose. Okay. In other words, I originally had two basis vectors that were E1 and E2, right? And then I had this new coordinate system that was U1. And if I wanted to keep the D dimensions, I would have had this guy U2 here, right? But I am ignoring U2 and I'm just projecting on the direction of U1 here. So I am losing this information in the direction of U2, right? So it's basically as if I am losing this orange vector here, this error vector here is kind of, it's exactly equal to the projection of my X onto direction U2, right? this is the error that I'm having. This is the information that I'm losing by ignoring U2 and just projecting onto direction U1. So in other words, my error vector is equal to the summation of the coordinates that I would have received if I projected onto directions or dimensions that are from R plus 1 to D, right? So my x prime is basically projecting x onto directions from 1 to R, and the error that I'm getting is the reminder of this projection of x into dimensions R plus 1 to D. We can see that this vector E or epsilon is actually orthogonal to our x prime in the original space, right? So the orange vector is orthogonal to this purple x prime. Okay, so geometrically, our goal in dimensionality reduction is not only, it's basically we have two different views that are equivalent to each other. That not only we want to find the direction that has the most variability in our data, but also we want to find the direction in which when we project our data onto, the error that we get, this orange error that we get, is as small as possible. So we want to find an R-dimensional basis that can give us the best approximation of x prime. So x prime is as close as possible to x for all the data points that we have in our data set. So we are trying to minimize the error for every data point that we have in our data set. So let's see an example here. Again, we have seen this is our D data matrix, and then these two are our original basis vectors, which are the standard basis vectors. We have seen that we can project onto U1 and U2. Now, consider that we are only projecting on U1 and we are not projecting on U2. If we only project on U1, then our new second row data is going to be equivalent to this vector. So minus 0.25 and 25. So how can we calculate that? We can either multiply the A21 with U1, or we can calculate U1 transpose and multiply P1 with the D2 that we had. So anyways, so D2 being this row. Now if we calculate the error, so if we calculate the original data difference, so the difference between the original data, which is -2 and -1.5, with the new projected data in the original space, or D prime, we are going to get to this, which is the error vector, -1.75 and -1.75. So as another example, in our iris data set, if we show our data in originally three-dimensional space, it's going to look like this. And if we want to find a one-dimensional subspace that is best representing our data, it's going to be a line, right? One-dimensional. It is going to be this line that is shown here in the direction U1. And then we can project our data points onto this line to represent our data. Again, we can see that there are errors, like these are the error that we get if we project onto U1, but U1 is the best direction. If I choose another line like this, I will get even more errors. If we want to look at the best two-dimensional basis for this data, so 2 dimensions means that it's going to be a plane. This is the plane that we are going to get. So we have 2 directions, U1 and U2, and we can project our data onto these 2 and have the minimum error possible compared to other 2-dimensional projections.